pleasure to welcome Isabelle Baraffe from the University of Exeter. She's the head of the astronomy department there, and she will be speaking to us about the frontier of exoplanetary modeling. And this is going to be very interesting, and as you all know, this is a highly exciting and rapidly evolving field of astrophysical sciences, so it is great that she could come and give this talk to us. A few words on her CV. She studied in Paris and went as an Erasmus student, so that is a great program, to Göttingen. So this is why she speaks perfectly German. And from that, she continued a bit further south from Göttingen to the Max Planck Institute for Astrophysics in Garching for her first postdoc. From that, she went back to Göttingen for another postdoc, and then she was hired permanently in Lyon. And eventually, in 2010, she got hired as full professor at the University of Exeter. And she is well known for her work in exoplanetary modeling, stellar physics, and modeling of stellar evolution. And she got many prizes in relation to this work. I think the most prominent one is the ESC prize.
Hopefully, ideas of what's going on modeling of exoplanets and where are the major efforts at the moment. And just here to show this, the organization of my talk, I will show that with this kind of scheme where I show interact structure. What I would like to show you is that there are now quite a lot of observational constraints for exoplanet regarding not only the internal structure but also the atmosphere. And I think it's important because I'm going to show you quite sophisticated numerical developments and theoretical developments, and they are now more and more constraints which actually justify this type of developments. And it will be even more and more GWT coming and ELT coming in the game. So first of all, for exoplanets, and now you know, I don't think I need to go to this general introduction about the number of exoplanets. You know that exoplanets are very common. We know about 3,000 already now. So planets outside our solar system are discovering more and more. So this is really very common here, the giant planets or rogue planets. And first of all, from planets that are transiting, so planets which are just passing in front of their star and in front of the telescope, we can infer the mass, we can infer the radius and the mean density if we have radial velocity and transit observation. We can also have information about the chemical composition of the planets just by looking at the light of the star which passes through the atmosphere of the planet. This is what we call transmission spectrum, and from there we can infer information about the absorbers in the planet atmosphere, such as water, potassium, sodium, methane, some other chemical species. Interestingly enough as well, for transit, the secondary transit is when actually the planet is going behind the star. Then we have information, we can have information about the thermal emission of the planet, and it's possible to derive brightness temperature map, which means that we can know, for example, how the temperature is distributed over the surface of the planet. Also, we have observational evidence for atmospheric dynamics. And, for example, phase curve observations show now that for some of what I call hot Jupiters, which are giant planets, which are very close from the parent star and they are transiting, so we are able to know that there is somehow the hotspot, I will explain that, is shifted eastward of the substellar point. To understand this, so just here you have the transit, and here you have the log curve of the transit. Then, what you can get here is that you get this phase curve, the orbital phase curve, where actually you have the relative flux of the planet to the star. Here, this is the transit, you can see here this gap. And then when the planet is turning round, you will have what we call the secondary eclipse, when the planet will just disappear. So you can see actually the day side of the planet, the one which is blocked by the star. So you see actually the brightness of the star increasing, and if the substellar point, which is just the point that receives most of the stellar irradiation, in principle should be just in the middle of your surface, yeah? And this means that when it just passes behind, you should actually have the highest temperature or the highest flux emitted by the planet, which should be here when it just disappears. But what you see is that there is a kind of shift of this hotspot, this temperature, and this is due to atmospheric dynamics. I will come to that. So this is also a very interesting constraint. And we have then, so I'll say here, shift of the hotspot because the maximum temperature is actually not happening here just when you have a secondary eclipse. Then we have also direct imaging. So this is a bit of a different technique, but this allows to have high resolution spectrum. And this is very, very useful for young planets because they are bright, but also this is very well known for brown dwarfs, where we have a lot of information of brown dwarf atmosphere. And brown dwarfs are kind of those failed stars which are can be in a planetary mass regime and do not burn stable hydrogen. We have also a new technique which has been developed by people, the group of Snellen in the Netherlands, Amsterdam and Leiden, where it's called the high dispersion spectroscopy, where they can have information on the chemical abundances of the planet, but also they may infer the winds at the surface of the planet. So this is another constraint of atmospheric dynamics. And finally, on the internal structure, we have, as I told you, mass radius from the transit from planet to planet. So here are transits, so observations, and those are models like the one I've developed in my collaboration, the transformer. And we can see here is that we have a huge variety of radius for a given mass of planet, like Jupiter mass planet, where we have a large fraction of what we call inflating gases exoplanets. And we have also objects which actually are heavily enriched in heavy material. Like here, this line, you can see there is one object here which can have a radius which can be explained by the planet having about 50% of water, which is a lot, a huge amount. So this is interesting because this diversity in heavy elements is important to link the planet composition with the formation process. And this is what people are using now to try to understand planet formation, inferring chemical composition of the planet. So now, just first part of my talk, I just want to mention briefly some problems regarding modeling the interior of giant planets. And if I'm more interested in giant planets, is first of all because we have much more observational constraints, and because there, the equation of state of hydrogen and helium, and also of heavy materials like water, silicates, and iron are very important, because the equation of state defines the thermodynamic property of your material, and it's what actually sets the mechanical property of your planet and therefore the radius for a given mass. And now there are absolutely fantastic progress which are made in physics with what I call first principle ab initio calculations of the equation of state. So those are not trying to be but really they are heavy numerical computations based on what we call so Monte Carlo quantum simulations, etc., which look at interactions between particles. And the planet is complicated. The planet like Jupiter is very complicated because you have non-ideal effects. You have partial linearity, you have pressure ionization instead of temperature ionization, which is kind of common in stars or interstellar medium. You have particle interactions, and you have also phase transitions which happen. And this is really tough problems on which physicists have been working for decades. And progress are just coming just because of this, and also because of lab experiments at very high pressure. The problem is that those ab initio equations of state which are now developed have been essentially applied to our solar system planets like Jupiter and Saturn, because we are getting important constraints from Juno, for example, and we are now getting, so this is a direct satellite sent to Jupiter, it's having constraints, we are going to have constraints on Jupiter's structure, and to a very high degree of accuracy. But this is still not possible for exoplanets, so there is still large uncertainty in the current interstellar structure. And for example, we don't really know what's the distribution of the heavy elements. You know, planet forming a disk, accrete planetesimal, accrete gas, but how are those heavy elements distributed in your planet? Is it in the core, the central core? Is it distributed everywhere? And most of show in my collaborators that this is actually, you may have also important effects if you change the distribution of your headlines. And I'd like to illustrate this problem with a very nice example here. This is a transit planet of 4 Jupiter mass, and with a very small radius, which can only be explained if you have a huge amount of heavy material there, which is 800 Earth masses of heavy material. Those are just the radius, and this is the age of the system, which is inferred by the star, and those are just the uncertainty ellipse. Here the green is the 1 sigma uncertainty ellipse. The problem is that you require a core in this type of planet, which is the maximum amount you would have in a kind of normal planetary, I would say, protoplanetary disk. So there is here a big problem. And we have shown that if you have a smaller amount of those heavy material, typically 500 Earth mass instead of 800, since this here, this red curve, those are all models, this is the radius as a function of time, you can reproduce the radius of your planet with a slightly smaller amount. But this is still a problem. And I think I challenge anyone who is doing planet formation, and I know that that's not here today, I challenge them to try to do planets with 500 Earth mass heavy elements. So the problem certainly resides in the equation of state that we are using, and hopefully when ab initio equation of state will be enough developed, we'll be able to test that and to see whether we can get a consistent answer for the structure of this type of planet. So this is the type of uncertainty that we have. Another very interesting problem, this is the mystery of inflating planets. And so I showed you that many planets have hot gaseous planets have a much higher radius than actually what is normal models and when we use standard models with standard physics can explain. And there have been a lot of, I would say, since the first eclipsing or transit planet, the probability mechanism is what I say incidence flux-driven mechanism. It's linked to the amount of irradiation received by your small planet from the star. And we see that because we can now measure the radius anomaly of many planets as a function of the planet temperature, which is also proportional to the amount of irradiation. And you can see that the higher the irradiation, the higher the anomaly. And if you actually still wait at the end of this talk, I will give you one of the scenarios that we very recently developed, and which is physically robust. And I think, of course, we are convinced that this is probably the best explanation for this type of puzzle. But to understand this, actually, we need to go through a bit atmosphere models and to understand also a bit of atmosphere modeling, because this is very linked to atmospheric circulation modeling of those type of planets. So what is going on at the moment regarding atmosphere models for exoplanets is first a lot of developments which are done in terms of 1D radiative transfer. 1D radiative transfer models are interesting because you can put much more physics than when you're doing Heidelberg transfer. People who do those kind of simulations know that. And currently, so those are very important as well because you can get the atmospheric structure, you can get photometry, you can get the spectrum of directly imaged exoplanets that go off. So now in Exeter, with the team of collaborators and of postdocs and PhD, we have developed ACMO, which is a code, which is a 1D radiative transfer model, which takes into account boundary capacities, which takes into account convection, which take into account chemistry, and we take into account not only chemical equilibrium chemistry, but also non-equilibrium chemistry, which is driven either by photochemistry, because you have actual photochemistry irradiation of the star at the surface of the planet, and this can be very important. And you have also some mixing which is happening. And we need this type of level of sophistication in the models to try to integrate observations. So here, non-equilibrium chemistry is induced in planets, but also ground walls by vertical mixing. Normally here, when you look at the fraction or the variation of elements of any kind of chemical species in an atmosphere as a function of time, you have a balance between the production curves and between the loss curves. This is not exactly the same. Chemical reaction is not a nuclear reaction, it's exactly the same process. The problem is that if you have some mixing, like vertical mixing, then actually you drive this out of balance and you have to take that into account. And we know that with this type of vertical mixing, which can be characterized by here this term and with a kind of turbulent can be, in some conditions, the chemical time of those reactions can be smaller, so much larger than the mixing time scale. And then you don't have any more equilibrium. And therefore you enter this regime of non-equilibrium chemistry. And we know from ground dwarf observations, these ground dwarf observations are very important because we know that this process exists. Because we see actually very cool atmospheres, for example, we show CO should not be there, or we see some hot atmospheres, we show methane, and methane should not be there. So this is the only way to explain it. And I just want here, I won't go into too much details, but here I just want to point out some of recent work we have been doing to show actually the importance of this non-equilibrium chemistry of the ground dwarf. And we can actually fit very well the spectrum of very cool objects with temperature less than 500 K with this type of non-equilibrium chemistry. We have shown also, we should test very recently as well, a kind of possibility to reproduce the spectrum of slightly hotter ground dwarfs that most of people explain with clouds, and we showed that actually we do not need clouds. I don't want to get into the details. For those who are interested, I'll just give you the references, but just to point out that there is still a problem in this field to know whether clouds in these objects are really very important to shape the spectrum. And this is very current and, I would say, topical research at the moment. So now, going back to contributors and to the main topic of my talk. So those 1D atmosphere models are important because they set atmospheric structure, which can be used then for initial models to do 3D hydrogen observations. So this is important. And also because we can calculate denser spectra for hot Jupiters for which you have observations. And here I want to point a difficulty that sometimes I would say the first models or the first modelers have kind of not necessarily ignored, but for a question of simplicity just is not taken into account. Which is that the first models which were done just did not calculate consistently your temperature pressure structure in your atmosphere models with your chemistry. But you do your chemistry, non-equilibrium chemistry somehow inconsistent with that processing. And we have shown recently that actually you cannot really do that. And I just want to illustrate this type of difficulty with, for example, a day-side average PT profile for a typical hot Jupiter, which is a kind of a 1 Jupiter mass model, which is very close to its parent star and highly radiated. And because it's locked, then you have a day-side. So here we have considered three typical cases where we have here a PT profile which is consistently calculated with equilibrium chemistry. This is here this dotted line. Then we have considered an inconsistent model where we took the same PT profile, but there we assume that you may have some non-equilibrium chemistry. And finally, we have a consistent case where the PT profile is somehow converged with your chemistry as well. And this is here those two cases where the non-equilibrium chemistry depends on this famous turbulent diffusion parameter, which is kind of parameter for now, which is kind of free parameter. And you can see that you may have a significant departure of the PT profile if you take this into account consistently. Now, if you look at the chemical abundances of this day-side profile, the chemical abundances are important because this is what is going to shape the spectrum. And therefore, it is what you're going to compare directly to observations. So there is a significant increase of methane, which is a strong absorber, and ammonia due to the vertical mixing. And here, this is what I showed. So this is the pressure of your atmosphere. This is the top of the atmosphere, and this is the bottom of the atmosphere. And here, this is the mole fraction. So this is the abundance of different chemical species. Let us here focus on methane abundance in case of chemical equilibrium, and here ammonia. And if you take into account non-equilibrium chemistry, you can see that there's a huge increase of your abundance of ammonia. Yeah?
I have a general question. What kind of boundary conditions do you have in your calculation of exoplanet atmospheres?
So here, for this time, we just fix the pressure, okay? And we fix here the interior, so the inner flux, which is coming, and we take into account, of course, the irradiation of the star. But here we usually we don't go much, so this is a 10 to minus 5 bar. So you see that astronomical chemistry. And if you turn that, for example, into some kind of observable to try to understand the effect here, so this big emission is kind of the photosphere where you will see this emission, just this radiation coming out. You have here this photosphere in case of equilibrium. This is at this level. In case of an inconsistent, non-equivalent chemistry with your PT profile, you can see that it will appear actually at much cooler and much higher pressure level. Whereas if you take that consistently, then you will have, actually it will be much closer than the photosphere that you will find when you have equilibrium chemistry. And the main reason for that is that this inconsistent model is actually violating somehow conservation of energy. So you are doing a wrong calculation. And the problem is that if you do use this to turn that into synthetic emission spectrum that you can then compare to observations if you have good and accurate observations, you can see that here this non-consistent calculation here in red strongly departs from the equivalent calculation and also from what should be correct, which is the green one. So the main conclusion is that it's kind of word of caution to say that non-consistent chemistry calculations can exaggerate the effects of non-equivalent chemistry, and therefore essentially you violate conservation of your energy balance in the atmosphere, and therefore people should be very careful when they use this type of non-consistent model and to compare to observations and to infer evidence, the evidence is really actually wrong. So that was one quite important thing I think that people should really consider when they want to do those 1D static atmosphere models. And now I will go to the last part of developments which are done in terms of modeling, which is the atmospheric circulation models, so dynamic models. And now this type of atmospheric circulation models is studied in the framework of what we call GCM models. So general circulation models or global climate models, some people confuse global circulation models, but anyways, GCM. And basically this is 3D hydrodynamics and radiative transfer, which is global, so on a full sphere. And the best tools for that are actually the tools that Meteorological Office, have been developing to study the weather and the climate of the Earth. So most of people, when they are doing this type of studies, and we as well, are using this framework of global circulation models. Those are important because it allows you to, first of all, to study the interaction between the high atmosphere circulations and deep layers, which may have an impact on the structure of the planet, but also it affects, this circulation affects as well the observations that you want to compare to HST observations or to Schweitzer and coming GWS and DLT. So you have to take into account the circulation. So just I want to illustrate here because they are a bit of, I realize that people consider GCM like a bit of mystery, or GCM is just weather forecast. But GCM is not more really than 3D radiative hydro models. And I just here some equations, typical equations that are used, not in all Met-Office scopes, but some of them are just conservation of mass, momentum equations in the planet's rotating frame, and then you have the energy equations where you have actually to take into account radiative process, the heating from the star, thermal conduction, eventually phase changes of water on the Earth, for example, that may be proposed also some other type of exoplanets. And here the coordinates, maybe people who are doing stellar hydro, for example, will not really use, but we use the longitude, we use the latitude, and we use also radar distance from the center of the planet. Then we use here the zonal wind, which is here this longitude wind. We use the meridional wind, which is here this latitudinal wind, and then we use the vertical wind. But this is typically, as I'm saying, change of reference and which is not of coordinates, but typical global relative time simulations. And what we have developed in Exeter is collaboration with the Met Office using and applying a tool which is called the Unified Model. We can do both weather and climate. Weather is short scale, 6 hours, 1 day, 3 days. Climate is on longer scale, 100 days, 1 year, 10 years, etc. And we have adapted that actually to the study of exoplanets, with here the green line printing, I would say, of collaborators of PhD astronomy and also metaphysics people. The main advantage of the Exeter UN is that it's really solving the Euler equations without any approximations compared to most of other studies which are done in the field applying to exoplanets. We do not, for example, assume hydrostatic equilibrium, which is done actually in most weather codes on Earth. We do not assume here kind of primitive equations, more kind of plan parallel approximation. And we allow the gravity to vary with times, which is not always possible in a modern GCM code, and this may be important to study, for example, contributors. And so this is very interesting because this tool can extend deeper than any other GCM codes currently available and can better account for better conversion. And I will show that this has some importance. We then have to couple that with sophisticated gravity transfer, and then we have developed something actually which is well used in the, I would say, the climate community based on the, we call the two-stream approximation and kind of correlated K method, which is opacity sampling method. Some people here with atmosphere models for stars know about that. And we need to use also state-of-the-art capacities, water method, etc. And there is a group in UCL in London who are actually calculating those molecular lines, very sophisticated molecular lines with billions of lines. So this is quite heavy stuff. And finally, you have also, of course, in chemistry for now, we include chemical chemistry, but we are currently implementing a chemical network in order to cover the chemistry as well. So when you apply that, for example, to hot Jupiter, typical transiting planet, what we find, for example, so when we look at the horizontal velocity after typically 1,200 days of simulations at a given pressure level, you see the kind of very strange structure, but here this is the longitude, and here this is the latitude of your planet. And what you can see is that typically at the equator you have a very strong, very fast west-east direction jet along the equator, and you can see the hot spot. So this is the hotter spot, which should in principle be at the substellar point, which means here at the longitude of 180, is just shifted toward east. And this is actually confirming the observations that I showed at the very beginning. This is actually, previous calculations have been showing that with some less sophisticated radius transfer and hydrodynamical code. So they show this is a quite robust feature of this type of calculations. The problem is that they're still, it's very complicated to understand what is really the physical mechanism which is giving this type of zonal jet. And we are trying to do some kind of linear stability analysis to do probably some cosmic waves or kind of other waves. So this is also something which is at the moment, I would say, very topical. But from those atmospheric dynamic calculations, then you can get synthetic phase curves, and you can then compare that to observations. So that's a very powerful thing, and it's really a product of those atmospheric calculations. For example, we get a phase curve here that we can compare. So this is the orbital phase, and this is here the ratio of the planet flux to the stellar flux. And this is here, for example, that is the observations, the observed figures at 4.5 microns. And this is the kind of here, the error bar, the shadow here. So this is the black curve. So here you see the day side, the highest emission of the planet, and here you see the night side of the planet. Here, this is in green, our synthetic calculations at 4.5. While we can reduce the day side flux of your planet, we are always estimating the night side. And we have tried to do many things actually, even changing the capacities, for example. And this is a kind of a robust problem. And we think that it can be either effect of non-human chemistry that we still do not take into account, which may enhance absorber elements of night side, or maybe some kind of supermetallicities. In all those calculations, of course, for simplicity, we assume that the planet has a solar composition. But we know from Jupiter, Saturn, that planets do not have solar composition. But the problem is that if we do not have any other constraints, the only thing we can do is to explore parameter range in different metallicities and try to see whether we can get constraints on the composition. That's that's a bit of the limitation. We need to have systematic exploration of parameters, but for that we need to have also the good and models which are enough sophisticated to make sure that the exploration of parameters makes sense. So we hope that the current implementation of non-linear chemistry we are doing at the moment in our GCN code will soon tell us and provide answers. So in the last part of my talk, I will come finally to this very new scenario and idea that we have, which is basically an idea of Pascal Grandin, previous postdoc in Exeter, and he has a position at CA in France, in Paris, which is actually the idea that scenario which shows that atmospheric circulation could explain inflation of those contributors, and there is, as I mentioned at the beginning, large fraction of those hot planets which are inflated. And I needed to go through all of this because actually the idea, understanding a bit of atmospheric circulation is very important to understand our scenario. So basically, the idea is to derive a set of 2D stationary solution of those 3D set of equations I showed you at the beginning. And we are looking for solutions where actually for the vertical velocity, for the zonal velocity, and also for the derivatives of the meridional velocity, and these are the equator. This allows us to reduce the equations to 2D and to look at what's happening at the equator. And what we found, and steady state is important because it allows us also to go and to look for a thermally relaxed state of the atmosphere, which is not currently possible with those 3D simulations, just because you would need to run them for a long, long time in order to see, for example, the temperature of the deep atmospheric value. And this is a problem of relaxation of many Heidelberg simulations having 3D. So in a steady state, we find that mass conservation implies that resulting longitudinal mass flow can actually be balanced. So a longitudinal mass flow can be balanced by a meridional mass flow and a vertical mass flow. And we need, because we have here a reduced set of equations, and to close the system, we need to assume some kind of geometry of the winds, longitudinal winds, so the zonal winds, which is driven, it is driven by irradiation, because you have anisotropic temperature heating. And therefore you have difference in temperature, difference in pressure, and with the conservation of longitudinal momentum, you are going to induce, with pressure gradient, you are going to induce wind circulation. But we need here to actually make some assumptions and give a geometry between the ratio of the meridional to the vertical mass flows. And here, this is what we have assumed the kind of parameter that we calibrate to our 3D simulations. So this is one of the assumptions which we have varied somehow, this parameter alpha, in the range of our 3D simulations. We find that actually this does not impact the effect that we find. But here to summarize what's going on, because it's a bit kind of complicated, I just want you to have a feeling of what's going on. So you have irradiation, you have temperature gradients, pressure gradients, zonally, along the equator. So the momentum equations longitudinally means that you have a wind which is driven by those pressure gradients. And the longitudinal, so you have longitudinal mass flow, because you have wind, of course. And because of mass conservation, then you will have actually mass flows which is meridional and vertical. So now, once you have this kind of dynamism to picture, okay, let's look at the inertia equation. And this 2D system of equations, this can be reduced to something where the main thing is to see that here you have terms which is terms of advection of a quantity which is called the potential temperature. This is a quantity which is very well known in climate studies, in Earth study, and that most of people who are studying climate use. This is a variable which is used here, and the potential temperature is typically the temperature that your gas would have. It moves theoretically to a given level of reference pressure P0. And here, so you have advection of this quantity, and this equals our picture is the derivative essentially of the radiative flux as a function of the vector of the radius. When you look at deep layers, you can even more reduce this type of equation here to here, a derivative of potential temperature as a function of the pressure, and you get here a term which in the deep layer actually is very, very small, just because the heating rate and your radiative transport is just very inefficient. So what happens is that in the deep layers, typically at pressure below 1 bar, then your potential temperature is constant. And when the potential temperature is constant, it means that actually your profile is adiabatic. So what it means then is that this vertical mass flux induced by the longitudinal mass flux drives advection of some potential temperature. And when you have this, it means that at depth, the atmosphere reaches a hotter adiabatic structure that could be inferred by 1D codes, by 1D atmosphere models, or by those 3D hydrodynamic models. So here, when I look at the type of profile we get for our 2D irradiated atmosphere, this is the pressure, top of the atmosphere, the bottom of the atmosphere, this is the temperature. Here what we get is that actually we get a hotter interior structure. And typically this hotter interior structure is what we would need in order to get the radius of those inflated planets. So to summarize, typically is that the main effect is that you have advection of this potential temperature, which forces the planet structure on the hotter adiabat, and because of this, you will prevent contraction of your planet. And this can be an explanation of your ample inflated planet. And when we apply now this adiabat that we find on evolution of planets, what we find here is that for a typical age of 1 million year, you look at the radius of those planets applying this adiabat, look at the evolution of the planet, and applying that, we get steady state 2D models, the radius which actually can explain the radius which is observed, and also this trend as a function of the flux, the irradiated flux of the star. And you can see here that when we use irradiated 1D model, then we get here this, which was the problem for many, many years. So that's, I think please have a look to this paper. I think you need to go through the equations to understand what's going on. Just to say that this advection of potential temperature is something which is well known in, for example, the Earth, stratified atmospheric layers, or in deep oceanic layers, where you have this type of anisotropic heating, which induce some longitudinal mass flow, and then you have vertical downflows in deeper layers, which can actually bring entropy and bring this potential temperature and adjust and warm up the deeper layers. So this is kind of similar process which happens, and it's well known in climate science. So I will just finish here with my conclusions, and I hope I somehow could show you some of the sophistication that are needed now in the field of exoplanet modeling, just because we are getting more and more accurate observations, and we're going to get more and more. We need, so it's very important to develop consistent 1D atmosphere models, and those non-consistent models, that is between PT profile and treatment of the chemistry, can be very misleading. It's very important also to develop dynamical models, and if you start to develop those, it needs to be also sophisticated for the interpretation of the data that are coming. Although GWST is going to be a revolution in terms of all the transitive data that we can obtain. And there is problem that we do not understand, which means that there is still a long way to go to try to understand the first observations that we have. And finally, the atmospheric circulation can explain the process of inflation of hot Jupiter with kind of quite a number of process which is advection of potential temperature. And I will just stop here and I'll say enough heat and enough talk, and let's cool down this quite hot atmosphere. And I thank you very much for your attention.
developments in planetary atmosphere, modeling and observations. The podium is open for questions. Who wants to start? Matthias.
In modeling the atmospheres, do you have to take phase transitions into account?
To take what?
Do you have to take phase transitions into account?
For the atmosphere, no. Well, it depends what you call. We have to take into account, for example, condensation, of course. So condensation of species in grains. So that's the next step that needs to be into account. For indeed, so it means that you have to take into account condensation of gaseous species into solid species, increased solid species.
I was also thinking about latent heat. Maybe about latent heat that may be released in the atmosphere.
Yeah, but for example, at the moment, we take into account kind of effects of possible condensate, like haze, very small pieces, or larger clouds, etc., through only, I would say, extra scattering and absorption coefficients. But then we need to do more and more sophisticated stuff, which is, for example, cutting that, some kind of ab initio dust growth model, etc., etc. This is also things which are on the way. Yeah, but that's the next sophistication as well. Yeah.
Wait. Okay, exercise now.
Hi, you made this very important point about the chemistry having to be consistent with the atmospheric profile and then have this non-proven chemistry. I wondered how easy is it to get a mixing strength profile which is consistent with the current atmospheric temperature profile that you look at. So because you had some free parameters for the mixing strength into the 9, 10 to 11. So is it because this is, I guess, another source of inconsistency where you have to be careful to get the right profile for the right temperature structure? Is that solved? Is that difficult to get?
Sometimes it's a bit painful because you need to have some, if you have kind of changes, brutal changes in the atmosphere of species like methane, etc. So you have to be, you have to be careful. And it took us a bit of time to get coverage models for this change in temperature. Yeah, but
So the KZZ value that you assumed that was then also derived from the model itself?
the KZZ is a free parameter. The KZZ is, I would say, something that comes from the hydro process. So in 1D, you just use values that, either values that have, I would say, been pseudo-inferred from some numerical considerations, but it's very difficult to get a diffusion coefficient from hydrodynamic considerations to ensure that you have the right solution, etc. Or it's more based on observations of ground walls, for example. So those are typical values that, for example, meet. But you don't have enough resolution now to trust any kind of diffusion coefficient you get.
In passing, you mentioned that the GCM model allows to go fairly deep into the planet. And you said this is important, but you later on didn't describe why and how. How does the depth of the layer that you actually simulate influence the result? If I understood you correctly with this remark.
Yeah, absolutely. This is important, first of all, to have the right vertical mass flux that we find, for example, and to have this type of transport. And the other thing is that it's important because ultimately what we would like to do is to go down the convective layer, to the top of the convective layer, because for now, there, we don't have, actually, we don't go deep enough to have convection, and we don't have resolution in those global simulations to be able to have convection like what you were doing, for example. Yeah, that's the next step, but I think it's really a question of resolution, and therefore speeding up the performance of those type of calculations in order to be able to go deep enough, and therefore at some point be able to have a good description of the deeper layers.
Yeah, in fact, this was behind my question, since I was always wondering about this very rapid zonal flows. on the one hand side. On the other hand, you have convection working in vertical direction, meaning also a lot of momentum exchange in vertical direction. In other words, viscosity. So is it clear that these strong vertical motions are not able to break down any zonal flow?
That's a very good point, but I think that we're not, at the moment, I don't think we're at the level where we can actually really say something about that. So there may be anticipation, but the point is that this, as I said, this super rotating jet is very robust to different schemes, to different assumptions. You can find it here also with the non-sophisticated radical transfer, kind of Newtonian forcing, etc., etc. So, and you exclude it. So it means at some point, first of all, convection is very deep. So this type of, motion you may get on this type of maybe practical, if you have relativity, maybe they are so important. Convection is much deeper than in rock, for example, that you have to
Very nice. So the Holy Grail would be a completely predictive model, at least a scaling relationship, and it seems to me that you would describe this physical causal chain between the superrotation, the jet, the need for mass conservation in 3D, the distribution between the meridional and radial flows, the alpha parameter, and then the advection of the potential temperature or heat, basically. And so it seems to me that would just give you some sort of scaling relationship that would tell you what the efficiency of heat transport is into the interior of the planet, the sort of epsilon value that people use when they do this for crude modeling.
But
So
not really exactly that. Because the epsilon, when you mention epsilon, is kind of extra energy.
it's the fraction of the irradiated heat.
Yeah. So it's a kind of source of energy. Here is different. Actually, it's not a transport of heat. It's not a transport of energy. What happens is that actually you force the planet at some point in its evolution to on the hotter area, and therefore you prevent the contraction. It's something
Right.
different than having an extra source of
But that transport is driven by,
but masculine, but additive. So there's
Sure,
no
it's-
transport of energy.
sure, but it's driven by the irradiance, which is driving the jet.
Yeah.
And it's the epsilon is scaling to the irradiance, the stellar flux, not to the internal heat of the planet. It's driven by it's scaling to the internal flux. So in that scheme, at least, it seems to me that there is a relation there somewhere.
Okay, I agree. Yeah.
It's
So-
not in the paper. I already looked, but
But
it's something that should come out.
yeah, I mean, the idea would be to indeed try to apply that or generalize that to all the stations and see that, and therefore have something that can use in the world.
So next question by Derek.
When you showed the discrepancies to the night side fluxes compared to observations, you seem rather convinced that it's due to opacities, missing absorption. If I understood that right, I mean, naively we could assume that also the overall flux is lower due to a larger temperature gradient, right? Even though with only one band, it's very difficult to say if the overall flux is smaller or if it's just the absorption in that particular band where you have observations.
So you say what, that it may be due just this discrepancy between the night side?
Yeah, basically my question is it excluded that the overall
You mean the opacity?
heat transport is overestimated, so you actually might have a larger temperature gradient between day and night side?
Well, of course, I mean, if you have a kind of cooler night side, then you will reduce. The problem is that what we get actually is what is cooled by the atmospheric dynamics, and therefore the circulation. And it's very difficult to get a really much cooler night side from those kind of simulations. So if you don't really change drastically, for example, the atmosphere, and the opacity with the dynamics.
Do you
It's my
have
feeling, yeah.
Do you have CO2 included in the capacities?
This is included as well, yeah.
And in the non, well, you don't
Yeah,
have.
this is not included to, yeah.
Are there further questions? Yes. More. Henrik.
So for these hot Jupiters, I guess it's always assumed they are tidally locked with a host star. So that means really everything, the whole interior is locked, or would that still allow for a kind of differential rotation in the radius direction? And could one model this actually?
That's a good question, because indeed, you can always imagine that you have, of course, at some point the planet has to converge everywhere towards the same agitator, which is by protection, this is full protected. Except if your planet is indeed having some kind of very strong differential rotation. That's a good point. There was some suggestion by models of burrows, etc., that we have some differential rotation happening. I don't think you can really very deep at some point, but it may be possible. That's open question. How to model that? Honestly, I think it will be very difficult to get some kind of spatial constraint on this. The only way is to remove observations and to see whether we can indeed drive some kind of differential rotation and shear, and what may be the impact. Because at some point at depth, you must converge to what is manual, because I don't see how, what it means. But yeah, that's the point.
Sorry for the uninformed question. Maybe it's because of the heat. What drives the convection in the first place?
The convection. Oh, this is very deep inside the planet. So this is actually the remaining, I would say, flux at the time of formation when the planet was.
So it's leftover heat.
Yeah, exactly. So this is just, and this is coming also from the contraction, and just release of the internal energy in PVT, so contraction and release of internal energy from the previous time when it was young and hot.
That's why I couldn't remember that.
Yeah, so yeah, it's just.
And with that announcement, let's come back to today's talk and thank Isabelle again for this wonderful overview of the current frontiers of atmospheric